Hi, in this video, we are going to continue the theory of ellipse. So in the last class, we understood what the ellipse curve was and what were the standard forms of the ellipse equation. Today, we'll start the discussion of tangents and normals and other similar properties of the ellipse. So let's begin. So let's say we have a standard ellipse here, x squared by a square plus y square by b square is equal to 1. And in this curve, I want to find the tangent at point P x1, y1. So equation of tangent at point P can be derived by doing the replacement method that I had suggested earlier for any conic. So what was the method? X square is replaced with x1, y square with y1, 2xy with x1y plus xy1, 2x with x plus x1, 2y with y plus y1, and the c constant is kept the same. So this method gives the tangent to any conic at a known point. So we apply that method here and we get the equation of the tangent as this: x1 by a square plus y1 by b square is equal to 1, right? This can also be obtained by the calculus method. So by calculus, you can find the slope of the curve at a particular point, and you'll get basically 2x by a plus 2y dy by 2x by a square, 2y dy by dx by b square is equal to 0. And from here also we get dy by dx is coming out to be minus 2x by a divided by 2y a square divided by 2y by b square. So this becomes minus b square by a square x by y. And if we want the slope at a particular point x1, y1, the slope is becoming minus b square x1 by a square y1. And then after that, we just put it in the point slope form and we'll say y minus y1 is equal to minus b square by a square x1 by y1 x minus x1. If you simplify this equation will turn out to be the same thing. You have to use the fact that this point lies on the ellipse. Therefore, x1 square by a square plus y1 square by b square is equal to 1. So this gives us two ways to find the equation of the ellipse if you know the point where you want to find the equation of the tangent, right? Either you do it by calculus or you write directly the form by the replacement method, right? What is the equation of normal? So equation of normal at P x1, y1 to the curve x square by a square plus y square by b square equals 1. And we follow the same method. In the previous derivation, we found out the slope of the tangent. And the slope of the tangent had come out to be minus b square by a square x1 by y1. We just now did that using calculus. So slope of the normal would obviously be a square y1 by b square x1 because the normal is perpendicular to the tangent. So now we'll write the equation of normal as y minus y1 is equal to a square y1 by b square x1 multiplied by x minus x1. And we can simplify this a little bit. So we can say multiply this b square x1y minus b square x1 y1 is equal to a square y1 x minus a square y1 x1, right? And we will get all the x and y terms on one side. B square x1 y minus a square y1 x is equal to b square minus a square x1 y1, right? And divide this by x1 y1, you will get b square y by y1 minus a square x by x1 is equal to b square minus a square. But actually, if it's just a standard ellipse, in a standard ellipse, a square is greater than b square. So this will turn out to be negative. So we reverse the sign of this. And we get a square x by x1 minus b square y by y1 is equal to a square minus b square. And this becomes the equation of normal to the curve at the point x1, y1, right? You don't have to remember this. It is always convenient to just calculate the normal equation depending on the situation, right? So don't try to memorize all of these formulas. These are simple derivations which you can do in the problem itself. Another form of the tangent equation, equation of tangent in slope form. We had seen that in parabola as well, we did the slope form of tangent equation. It was mx plus a by m, if you recall. Here, let's say the slope of the tangent is given as m, and the equation of the ellipse is this. So we want to find the condition basically that the line y is equal to mx plus c is tangent to the curve. In order to get that condition, we follow the same method that we learned in the parabola chapter. And what we do is we substitute this line equation into this curve equation. And we say that the resulting quadratic should have equal roots, has discriminant equal to 0, because the line is supposed to touch the curve and it's not intersecting the curve. If it was intersecting the curve, the roots would be unequal and therefore discriminant would have been positive. So we can do that here now. We can say x square by a square plus mx plus c whole square by b square is equal to 1. Multiply by a square b square everywhere. B square x square plus a square m square x square plus a square c square plus 2a square mcx is equal to 1. Is equal to a square b square actually, if you multiply by a square b square throughout. So we are getting b square plus a square m square x square plus 2a square mcx plus a square c square minus a square b square is equal to 0. And now in this relationship, we have to say discriminant equal to 0. This is a quadratic whose discriminant is 0. And when you calculate the discriminant, it turns out that you will get, let's see what happens. You'll get 4a power 4 m square c square minus b square plus a square m square multiplied by a square c square minus a square b square is equal to 0. So we will be able to cancel one a square. So you'll get 4a square m square c square minus b square plus a square m square multiplied by c square minus b square is equal to 0. And let's simplify this. So from here we get a, oh wait, I missed a 4 here because there was b square minus 4ac, so 4 here, and 4 can be cancelled. So we get a square m square c square minus b square c square plus b power 4 minus a square m square c square and plus a square m square b square equals 0. So this gets cancelled. And now in all of these three terms, you can cancel a b square. So you get b square minus c square plus a square m square is equal to 0. And from here we get c square is equal to a square m square plus b square. So the c value can be plus or minus root over a square m square plus b square. And if we get a condition on c, we know the equation of the line, what it will be. And you will get basically y is equal to mx plus or minus root over a square m square plus b square is tangent to the ellipse x square by a square plus y square by b square equals 1. And notice that there are two different constant values here. There are two tangents that are present here with the same slope. So what that means is if you have an ellipse like this, there is one tangent with slope m, and obviously there will be another tangent somewhere here with the same slope. The c values are different. This is, let's say, minus root a square m square plus b square. And here for this line, the c is plus root a square m square plus b square. So you should be aware that there are two tangents having the same slope, right? So that is an important condition. Now, from the same condition, we can now say that a line touches the ellipse. What line? Y is equal to mx plus c touches the ellipse x square by a square plus y square by b square equals 1 if and only if c is equal to plus minus root over a square m square plus b square. If, for example, c was less than a square m square plus b square, right? Or you can say between these two values. So basically, if c square was less than a square m square plus b square, in that case, the line intersects the ellipse. Line does not meet the ellipse, does not meet the ellipse, so no intersection. Because the discriminant will come out to be less than 0 in that case. And if c square is greater than a square m square plus b square, then there will be 2 points of intersection. 2 points of intersection, because in that case, the line will cut the ellipse twice at two different locations, right? So that is something that you should be aware. Again, you can also prove that from any point, there can be two tangents that can be drawn to an ellipse from an external point. If you have an ellipse like this, and this is a point h comma k, it is possible to draw two tangents to the ellipse from here. Just like in parabola, we can prove this statement. It is similar result for a parabola as well. Another concept that you need to be aware of here is the concept of director circle. Director circle is basically locus of the point of intersection of perpendicular tangents to an ellipse. Point of intersection of perpendicular tangents to an ellipse. So if the point is B h comma k, and I'm saying this is the point of intersection of two tangents drawn to the ellipse, x square by a square plus y square by b square equals 1. The equation of the tangents would be y is equal to mx plus minus root over a square m square plus b square. And this tangent has ph comma k on it. So therefore we can say k is equal to mh plus minus root over a square m square plus b square. And we can write it as k minus mh whole square is equal to a square m square plus b square. And now we are getting a quadratic in m. You're getting k square plus m square h square minus 2m kh is equal to a square m square plus b square. And if you make it a quadratic, it is m square h square minus a square minus 2kh into m plus k square minus b square is equal to 0. So this quadratic's existence shows us that there are two different tangent equations that can be drawn from PHK to this ellipse. And now what we will say is that if these two tangents are perpendicular, then m1, m2, which is the product of the roots in this equation, should be equal to minus 1. This is an equation on the slopes of the tangent. So if the two tangents are perpendicular, the product of their roots, product of those two tangent slopes will be equal to minus 1, right? So here we can say that product of the roots here is a square minus b square by h square minus a square, which is c by a, which is minus 1, which means k square minus b square is equal to a square minus h square. And if you bring everything to one side, you get something like this. And this is the condition that makes sure that the two tangents drawn from h comma k are perpendicular. So if in order to get the locus, we'll replace h comma k with x and y, and you'll get the locus of the curve as x square plus y square is equal to a square plus b square, which is known as the director circle. Notice that this is a circle with center 0, 0 and radius root over a square plus b square. And the center of the director circle is same as the center of the ellipse, right? So that is something that you need to be aware of. Then another idea that you need to know is the concept of auxiliary circle. So if you have an ellipse like this, x square by a square, x square by a square plus y square by b square equals 1, where a is greater than b, we can make a circle here with the semi-major or with the major axis as the diameter. Basically, the equation of the circle that we are talking about is x square plus y square is equal to a square. This circle is known as the auxiliary circle. The center of the ellipse and the center of the auxiliary circle are the same. It is 0, 0. The radius of the auxiliary circle is a, whereas a was the semi-major axis of the ellipse. We will see the application of this auxiliary circle when we look at the parametric form of an ellipse and how to represent a point on the auxiliary on an ellipse in a parametric form. So we will understand how we do that here. So for example, I want a point P x1, y1 on the ellipse, right? So instead of x1, y1, I want to express it as a parameter. So what I will do is drop a perpendicular from the point to the major axis. And this perpendicular line you should extend upwards. And downwards also you can extend. And this perpendicular line will meet the auxiliary circle x square plus y square is equal to a square at a certain point P dash. If you join O to P dash, which is the origin here, to P dash, you should realize that here the x1 is the same coordinate here, but x1 coordinate is the same as the x1 here, but the y is different. It is y1 dash, right? So if this angle is theta, what we can say is this point would be a cos theta, comma a sin theta. But correspondingly, this point P would be a cos theta, comma b sin theta. Because if you put a cos theta in the ellipse equation, y comes out as b sin theta. So the theta angle that we are talking about here is the angle made by a point on the auxiliary circle with the major axis. And because we know the parametric representation of any point on a circle, it is a cos theta, a sin theta. From there, we figured out that the x coordinate of point P is a cos theta. And if x coordinate of point P is a cos theta, then y coordinate becomes b sin theta. So another way to write a point P x1, y1 on an ellipse, on a standard ellipse, is to write in terms of a cos theta, comma b sin theta. And that parametric representation is useful because it reduces the number of variables that you have. Number of variables that you have are not x1 and y1 or two variables, it becomes a single variable, which is theta, right? So this parametric form idea is super important. And let's look at some other results. So chord of contact equation. The same way as we did it in parabola, in ellipse also the definition of chord of contact is simple. If you have an external point P, H, comma K, from here you draw two tangents to the ellipse. Let's say they meet at Q and R. The line joining QR is known as the chord of contact. And the equation of the chord of contact is the equation of the tangent to the ellipse from the point H, comma K. Actually, H, comma K is not on the ellipse, but the equation of chord of contact comes as if you can take H, comma K as lying on the ellipse and write the tangent equation as xh by a square plus yk by b square equals 1. This equation is actually the equation of the chord of contact. Similarly, like in the previous chapter, we can also find the equation of a chord with a given middle point. Chord with a given middle point. Let's say the given midpoint is x1, comma y1, and the other points of the chord are not known right now. We just know the midpoint of the chord, x1, comma y1. So similar to the proof that we did in the parabola section, you can try a similar proof here. The equation of this line will be t is equal to s1, where x square by a square plus y square by b square equals 1 is my equation of the ellipse. So the t equation will be written with reference to this point. It will be x1 by a square plus y1 by b square minus 1 is equal to s1, which will be x1 square by a square plus y1 square by b square minus 1. So the equation of chord with a given midpoint becomes this equation. This is the equation that is desired. Okay, now we come to some of the things that we can derive using the parametric form of the ellipse. So the first thing that you have to remember using parametric form is the equation of a random chord on the ellipse. So this is my ellipse x square by a square plus y square by b square equals 1. Let's say I have 2 points that are being joined, P and Q, and the coordinates are theta 1 and theta 2. What is the meaning when I say theta 1 and theta 2? P would be a cos theta 1, a b sine theta 1, and Q would be a cos theta 2, b sine theta 2. These are P and Q. We can show by doing simple 2-point form straight line equation and simplification using trigonometric results. We can show that the equation of the chord PQ will come out to be x by a cos of theta 1 plus theta 2 by 2 plus y by b sine of theta 1 plus theta 2 by 2 is equal to cos of theta 1 minus theta 2 by 2. There is no shortcut to get this equation. All you have to do is write the equation in 2-point form. These are the 2 points. Write the equation of the straight line connecting them, right? This equation has to be remembered because you will not have time to do the trigonometric simplifications in the exam, right? So keep in mind that this equation has to be remembered. It's the equation of a chord in parametric form. We can show some extra results using this as well. So what I want to show is if the chord joining 2 points whose eccentric angles, when we say eccentric angles, we mean theta 1 and theta 2, the parametric angles, are alpha beta. If the chord joining 2 points whose eccentric angles are alpha and beta cuts the positive major axis of the ellipse at a distance c from the center, at a distance c from the center, then you can show that tan alpha by 2 times tan beta by 2 would be equal to c minus a by c plus a. So this is a result that can be proved using the parametric form. So the equation of the chord would have been x by a cos of alpha plus beta by 2 plus y by b sine of alpha plus beta by 2 is equal to cos of alpha minus beta by 2. This is the equation of my chord. Now it cuts the major axis at c comma 0. So you can put y is equal to 0 and c here. You'll get c by a cos of alpha plus beta by 2 is equal to cos of alpha minus beta by 2. And now it's a matter of simplification. C by a is equal to cos alpha minus beta by 2 divided by cos alpha plus beta by 2. What I would do is componendo and dividendo with c minus a by c plus a becoming equal to, you can see cos minus cos would be 2 sine on top. And cos plus cos here would become 2 cos alpha by 2 cos beta by 2. And this expression is clearly tan alpha by 2 tan beta by 2. So we can prove that result here. Again, we can find tangent and normal equations to an ellipse. So if my ellipse is like this, I can find tangent and normal equations in terms of the parametric points. The point is a cos theta, b sin theta. So equation of tangent will become x into x1. So a cos theta by a square plus y into b sin theta by b square equals 1. The equation of tangent becomes x cos theta by a plus y sin theta by b equals 1. An equation of normal, if you recall, would be, you can use the direct form a square x by x1, that form. So let's use that directly, or we can do the normal straight line method also. So I will use the direct form itself. The equation of the normal was a square x by x1 minus b square y by y1 is equal to a square minus b square. So this becomes a square x by x1 is what? A cos theta minus b square y by b sin theta is equal to a square minus b square, right? So this equation is basically ax by cos theta minus by sine theta is equal to a square minus b square. This is the equation of normal at a parametric point, right? Okay. Then there are some concepts that are concepts like co-normal points, which will be better understood through some examples. So co-normal points is a concept that I will discuss through some problems. So what we will do is, actually, there is not much theory left. This is the important stuff that you need to know. So we have been able to roughly cover the theory of the chapter in 2 classes. In the next couple of videos, I will do some problems on ellipse to make sure that all of the stuff that we have discussed is completely clear and refreshed in your memory. So look out for those videos. We'll do a lot of problems in the next couple of videos on ellipse and make sure that it is completely solid. So stay tuned for the future lectures in the series. After ellipse, we'll go to hyperbola and we'll finish the coordinate geometry by doing circles and straight lines as well. So over the next couple of weeks, I intend to finish the coordinate geometry revision, and hopefully you are learning and revising for your JEE Advanced through this course. If you like the content, please like the video, subscribe to the channel, and support the channel and help it grow. All your help is super welcome, and I appreciate that a lot. Thank you. I'll see you next time.